In this chapter, we're going to be talking about this really hard to pronounce word. This word here is called stoichiometry. Stoichiometry. Stoichiometry kind of reminds me of baking. So I'm going to bake some cookies for us to enjoy in class tomorrow. Okay, so I have no idea how to bake cookies, but if I followed an instruction list like this, I would make a batch of cookies. Let's pretend this list of ingredients made 5 cookies. But if I wanted to make 10 cookies to share with you, I would have to double the ingredients. If I doubled every single one of these ingredients, I would get double the amount of products. Same thing happens in chemistry. In chemistry, we have ingredients, but we call them reactants, and then we have cookies or end products of our baking. We call those products. And you can manipulate the reactants to get the desired amount of products. And we could also use these numbers in mathematical calculations to determine all kinds of things in the chemical reaction. So stoichiometry is actually a Greek word, and it means measuring elements. It's defined as the calculations of the quantities in chemical reactions based on a balance equation. We're going to get into some of these calculations in the next couple of videos, but before we do that, let's talk about how to interpret equations. Before we start manipulating the variables and the values and the math of some of these equations, let's talk about how to interpret a chemical equation. There's 4 different ways. One way is in terms of particles. An element we know is made up of atoms. It's the smallest form of an element that is just that type of element. It would be one atom. A molecular compound is made of only nonmetals. So a nonmetal bonded to a nonmetal, and they're made up of something called molecules. So the smallest particle of a molecular compound would be a molecule of that compound. And an ionic compound, which is something that's a metal bonded to a nonmetal, they're made up of something called a formula unit. So the smallest part or particle of an ionic compound is a formula unit. So if we're interpreting a chemical equation in terms of particles, we need to really slow ourselves down and stop and think, is this an element? Then it's made up of atoms. If it's a metal bonded to a nonmetal, then it's made up of formula units. If it's nonmetals bonded to nonmetals, then it's made up of molecules. So let me show you what I'm talking about. Let's interpret this equation in terms of particles. So the coefficient 2 here in front of this number means I have 2 of this, H2. But then we need to ask ourselves, what is H2? Is H2 an element? Is it a molecule? Or is it a formula unit? And this one's actually kind of tough. The answer is it's a molecule, because hydrogen is an element, but we have H2. That's a hydrogen bonded to a hydrogen. So all the diatomic elements, like hydrogen, we would use the term molecule. So we have 2 molecules of hydrogen, and we're going to react that with this oxygen here. Now there's no coefficient in front, but we know that if there's no coefficient, that really means there's a 1 there, or else we wouldn't write O2. If there wasn't at least one of them, we wouldn't write it. So we have 1, and again we'd use the term molecule, because again it's a diatomic molecule. It's not an element of oxygen, it's a molecule of oxygen. And then we have the arrow. When we get to the arrow, we read that as form. So one two molecules of hydrogen and one molecule of oxygen form to make, and we see that coefficient 2 again. So we have 2, and then we have H2O2 water. So again, stop, slow yourself down and think, is this an element, a molecule, or a formula unit? Well, I know it's not an element because I have multiple types of atoms here. And I have a nonmetal, hydrogen, despite the fact it's in group 1, it's still a nonmetal, it's a gas, bonded to oxygen. So this is a molecule. So again, another molecule, two molecules of water. So this is the equation in front of you interpreted in terms of particles. So we're basically just reading it, but we're stating how many particles we have here. I have two molecules of hydrogen and one molecule of oxygen, and they're reacting together to form our products, which is two molecules of water. Let's try this one here. So we have 2, and then I have Al2O3. So again, slow yourself down and stop and think. Is this an element, a molecule, or a formula unit? Well, I know it's not an element, and it's not a molecule either, because this Al, this is a metal. It's a metal bonded to oxygen, which is a nonmetal. That's indicative of a ionic compound. So this is two formula units of Al2O3, aluminum oxide. And they're going to decompose. I'm using the word decompose because I know this is a decomposition reaction. I only have one reactant and it's breaking down into two products. So it's going to decompose into 4, and then I have atoms. I'm going to use the term atoms here because I just have aluminum. There's nothing bonded to it. So 4 atoms of aluminum and 3 molecules, because it's diatomic, oxygen bonded to oxygen, 2 nonmetals, is a molecule, 3 molecules of O2. You try this one. Go ahead and pause the video, write this formula down in your notebook, and when you're ready, unpause it and you'll see how you did. Okay, we have 2 atoms of sodium. We use the word atoms because it's just Na, just sodium, nothing's bonded to it. And 2 molecules of water. Molecules is the term we'll use because it's a nonmetal hydrogen bonded to a nonmetal oxygen. And they're going to react to form 2 formula units of sodium hydroxide. We use formula units because Na is a metal. It's a group 1 alkali metal bonded to 2 nonmetals here. This is a polyatomic ion hydroxide. And our other product is 1 molecule of hydrogen. Okay, the other way to interpret chemical equations is in terms of moles. This one is a lot easier. You're going to like this one. The coefficient tells us how many moles of each substance there are. So remember, a balanced equation is a molar ratio. So you just pretty much need to read the coefficients here. So let's interpret this equation in terms of moles. I have 2 moles of Al2O3. The big 2 in front of this tells me I have 2 moles of this formula unit. And it's going to decompose into 4 moles of aluminum and 3 moles of oxygen. So all you really need to do is read the coefficients from left to right. This one's really easy. You try this next one. Okay, 2 moles of sodium and 2 moles of water are going to react to form 2 moles of sodium hydroxide and 1 mole, remember if there's no coefficient, it's really a 1 mole of hydrogen. Okay, the third way to interpret chemical equations is in terms of mass, and this one is the one that's going to actually require the most work by you, so you're going to need your calculators handy for this one. The law of conservation of mass applies to every chemical reaction. We've talked about it before. It says that no mass is created and no mass is destroyed in a chemical reaction. We can check this mass by using the moles that's given to us in the balanced chemical equation. So here's a balanced chemical equation. We have 2 moles of hydrogen and 1 mole of oxygen reacting to make 2 moles of water. So we need to do some math to show that the mass on the left is equal to the mass on the right. And there's multiple ways to do this, but I'm going to do the bracket method that we've used before because this bracket method is going to become really important in this stoichiometry chapter. So although there are other ways to do this, please try this bracket method for this type of problem because it's going to help you out later, trust me. Okay, so we're going to start with what we know. We know we have 2 moles of H2. It says so in this balanced chemical equation. And then we're going to set up a bracket to convert from moles of H2 into grams of H2. So on the bottom, I'm going to put 1 mole of H2 because I want moles on top to cross off with moles on the bottom, and I want to turn it into grams here. The number I'm going to put on top here is the molar mass of H2. So if I go to my periodic table and check hydrogen, it says hydrogen weighs 1, but I don't have hydrogen, I have H2, so it's going to be 2 grams of H2 for every mole of H2. Okay, so moles of H2 and moles of H2 will cross off, like I said. I'm left with grams of H2, which is what I want. I want to convert all of these moles into grams and compare the left to the right. So it's time to punch it in. 2 times 2 is 4. You probably don't need to punch that one in. That's easy. Okay, then we're going to do it again for oxygen. According to our balanced equation, we have 1 mole of oxygen. We go to the periodic table, 1 mole of oxygen atoms weighs 16, but I don't have an oxygen atom, I have an oxygen molecule. So 16 times 2 is 32 grams. So moles of oxygen will cross off with moles of oxygen and convert to grams of oxygen. So the math is just 1 times 32 is 32. Okay, so these are the two on the left. 32 plus 4 is 36 grams of reactants. So here's that equation again, and I've just written 36 grams on the left side so I remember it here. We're going to do one more math problem to make sure the mass of the right side is equal to the mass of the left side. So start with what you know. You know there's 2 moles of water from the balanced equation. We're going to set up a bracket to convert from moles of water into grams of water. In order to do that, you need to know the molar mass of water. So let's figure it out. The mass of water is going to contain 1 hydrogen. It's going to contain 2 hydrogens because the formula is H2. So hydrogen weighs 1, but there are 2 of them. So 1 times 2 is 2 grams. And the mass of water is going to contain the mass of 1 oxygen because there's 1 oxygen in that formula. So oxygen weighs 16. So if I add that together, 16 plus 2, I get 18 grams per mole. So on the top, I'm going to write 18 grams of water for every 1 mole of water. So moles of water and moles of water cancel, and now I just need to multiply everything on the top and divide by everything on the bottom. So 2 times 18, and I don't need to divide by 1 because that won't change my answer. 2 times 18, of course, is 36, and we can see that the mass of the products on the right, 36 grams, is equal to the mass of the reactants on the left, 36 grams. Okay, why don't you try this problem? Using the same method we did, you're going to need to do 3 small math problems. I want you to find the mass of the aluminum oxide on the left, and then the mass of the 4 moles of aluminum and the 3 moles of oxygen on the right, and show that they are both equal. So go ahead and give that a try, and when you're ready, I will solve it for you. Okay, so first step is we'll do the reactant, 2 moles of Al2O3. So in 1 mole of Al2O3, we have 2 aluminum, so 2 times 27 is 54. And then we have 3 oxygens. Oxygen weighs 16, but 16 times 3 is 48. If we add that together, we get 102 grams per mole. So I'll plug that in the top. My moles and moles of aluminum oxide will cross off, and 2 times 102 is 204 grams of aluminum oxide. Okay, now let's do our products. I have 4 moles of aluminum. I can easily look up aluminum on the periodic table. Aluminum weighs 27. 4 times 27 is 108 grams. So I'll plug that in there just so I have it in front of me. And then lastly, we need to convert 3 moles of oxygen into grams of oxygen. So we'll set up another bracket, put moles on the bottom so it will cancel off, and put the grams of oxygen in 1 mole of oxygen. Remember, oxygen is O2, so 16 times 2 is 32 grams. 3 times 32 is 96. Okay, so if 108 plus 96 is equal to 204, you know you are correct. And of course, it is. So when I'm asking you to solve these types of problems, I like to see some kind of statement like this. 204 grams equals 204 grams, maybe a little check mark to show that you know that these things are the same. Okay, the fourth way to interpret a chemical equation is in terms of volume. So at 1 mole, any gas at STP takes up 22.4 liters of volume. So if I have this equation here, these are all gases. It doesn't say it, but let's say they're all gases, and let's pretend they're at STP. We can interpret this in terms of volume. So I have 2 moles of hydrogen, so 2 times 22.4 would be 44.8. And I have 1 mole of oxygen, so that would just be 1 times 22.4. And on my product side, I have 2 moles of my product, so 2 times 22.4. I would have 67.2 liters of reactants, but only 44.8 liters of products. And you can see that volume is not conserved in a chemical reaction. They are not equal on both sides of the equation. Mass is, atoms are, volume is not. So in summary here, you should know a few ways now to interpret a chemical reaction. Interpreting a reaction in terms of mass is the only one that you need to do work for on the calculator. It's the only one you need to show your work and do some math. The other ones you just need to be able to do. And the good thing about interpreting in terms of mass is you can always check your answer by applying the law of conservation of mass. And if you know how to convert from grams to moles, or actually from moles to grams, this should be no problem for you.